Okay, it's a great pleasure for me to be here and a great honor to talk in this first session of the festival, Passion for Knowledge. And I would like to thank the organizers and for this fantastic opportunity which is given to me to participate in this event. I would like to talk to you today about truth in science. I would like to talk about the way truth is emerging from a permanent exchange between observations and the elaboration of theories, and how it evolves, how truth evolves when scientists get new knowledge from more advanced technologies. I think it's very important to talk about this today because we live in a very strange and paradoxical time. It's fair to say that science has had great successes in the past. It has allowed us to understand a lot of things, to acquire knowledge about fundamental effects, and at the same time, it has given us a lot of power over the world. From science, we have seen a lot of new technologies. We have learned to compute, to communicate in much better ways than before. It's a revolution which has changed our lives in all fields, not only in physics, but also in biology, in medicine, in agriculture, and it also promises to be very important in the future because, as has been said before, we are facing a lot of challenges, and these challenges can only be solved if we get more science. So there have been a great success, but nevertheless, these successes were not enough to protect science against the flourishing of lies, of fake news, of alternative truths, of conspiracy theories, which have emerged during these last years. And of course, all these attacks are not only against science. We have this in the field of politics also, but science is especially vulnerable because these conspiracy theories are based on a very pernicious or a very perverse kind of doubt, a doubt which applies to everything which is scientific, and this kind of doubt is exactly the opposite of the rational and the constructive doubts that scientists have to use to build their theories and to build and to promote their discoveries. So this is a big problem, and I think we have to address it. I am not a sociologist, but of course there are many explanations to these problems. We live in a global society, and individuals feel threatened by this globalization. People who feel that they are left on the side of the road, that they are not protected anymore from competition, have fears, and these fears push them to gather into a kind of tribal communities, to exchange ideas between them, and to promote cultural and religious particularisms, which make them completely insensitive to what's taking place outside of their bubble. And I think the problem of science is that science is universal. Science is a global activity, and as a global activity, it is threatening them too. And that's the problem that science is facing. There are many examples of this kind of conspiracy theory. There is one about climate change, which says that climate change is in fact an hoax which has been invented by Chinese to weaken Western economies. This is a kind of conspiracy theory which has been carried by the President of the United States. So it's a very serious problem. There are also conspiracy theories about the danger of GMOs and about the danger of vaccines, which are supposed to be poisons which are imposed on people by lobbies, pharmaceutical companies, and problems like that. So we really have to face these very serious problems. And moreover, these problems these kind of conspiracy theories thrive because they occur in a context of cultural relativism. There are a lot of people who say that, in fact, science is not an objective thing, that science is a kind of social construction. And if you admit this idea that science is a social construction, then any opinion is worth any other one, and then everything is open for a denial of scientific thought, and I think this is very bad and very serious. So we need to fight against that. And the only thing that scientists can do is to try to tell to the general public what science is about, what are the values of science, and give historical examples about the way science is building up truth and knowledge. And the previous talk was a very good example of that, and I will try to give you other examples of the way science, the way truth is building up, and what are the advantages of having science thriving in society. So I will talk about, first of all, I will try to define what is truth in science, how can you define it. Then I will discuss how truth is an evolution, is a notion, is a concept which is evolving in time, and how it is permanently questioned by observations and experiments. Then I will talk about the power that science gives us, the power it gives us to be able to do things which were impossible before. And so this is a kind of proof by the usefulness of science. There is something true in science because science gives us a power on nature which a conspiracy theory will never give us. I will talk also about what I call the connectivity of science, the fact that different fields of science are connected with each other, and if you try to change one of them, you have to be careful not to jeopardize the connection between the different areas of science. I will talk about the universality of science, and finally, I would like to discuss the difficulties, one very serious difficulty of science, that it unveils aspects which are counterintuitive. When you look into a scientific theory, you find that things which seems to be obvious in everyday life are not really obvious. You have to go below, you have to go behind the common wisdom to understand really what science is about. And this confrontation with the illusion and biases of our intuition is a very important point, and we'll see that even scientists have to face this kind of problem. And finally, I would like to say a few words about what we can do to protect science, to defend the values of science, and the connection with education. So let's start with the definition. What is the truth in science? And I think there are two aspects of that. There is first the truth of facts. For thousands of years, men and women have been observing the sky, and just by observation, by looking at the position of the star and the planets, you get some knowledge. These are facts. Everybody can check them. The second aspect of facts is the fact that you can reproduce things in the laboratory. You can reproduce things on Earth. You can try to study some phenomena and to make quantitative measurements. This is, for example, a picture which shows Galileo experimenting the free fall and the fall of balls along an inclined plane to discover the laws of gravitation in this experimental way. So what can we say? The facts are validated by the fact that everybody can reproduce them. When you write a paper in physics or in biology or in any field, you have to write in the paper the way you did the experiment so that anyone could, in principle, reproduce your results. So in this respect, there are no fake news in science. It is very different from other fields. Of course, some people are cheating, but if you have a fake paper, it's very quickly one recognizes that it's a fake. These two aspects answer to a very simple question. Observation answers the question what it is about, what happens around us. This is observation. Experiment answers the question how does it happen? For instance, you see that balls are falling, so how do they fall? What is the law of the fall? And Galileo found that the distance that a ball is falling is proportional to the square of time. So this is a measurement which answers to the question how. But after the questions what and how, there is a third question, of course, which is where theory comes about, the answer to the question why. Why do for example, balls fall in such a way that the distance is proportional to the square of the time of the fall. And then theorists come into play. And of course, the answer to that question was given by Newton by the gravitational laws. He had just one equation which explains how objects fall on the ground and how planets move in the sky. And with a single equation, he gave an answer to these two problems which up to Newton were not supposed to be related to each other. The fall of an apple from a tree or the motion of the moon around the Earth were supposed to be two phenomena which had nothing to do with each other. So this gives you the first idea about the truth of a theory. A theory should be unifying. A theory should give a common explanation to events, to phenomena which before that were supposed to be disparate. And this is also called reductionism because you use only a very small number of parameters to explain a lot of things. In the case of gravitation, you just need one equation which tells how objects attract each other by the gravitational law. So this is one example. Another example is, of course, electromagnetism. 2 centuries after Newton, Maxwell unified with a set of equations electricity, magnetism, and optics. He just discovered that light was an electromagnetic wave propagating through space at the velocity of light, and this was another big unification in science. So theories are true when they are able to unify disparate things. They're also true because they are predictive. They predict new phenomena which were not understood or were not observed before. For example, one big triumph of Newton's law was the discovery of the planet Neptune by the French astronomer. I think he was a royal astronomer in France in the 19th century, Le Verrier, and independently by Adams in England, who discovered by looking at the motion of the planet Uranus that it was moving in a way which could not be explained by Newton's law if you take only into account the known planets. So they had the idea that there was an unknown planet which the calculation allowed them to pinpoint in the sky, and this planet was discovered, and it was Neptune. So this is a big triumph of the gravitational theory. And in the case of electromagnetism, the big triumph was the fact that Maxwell's equation predicted the existence of long wavelength radiation, which were found by Hertz to be radio waves, and also very short wavelength radiations that Röntgen discovered, which were X-rays. So you see that the predictive power of the theories is also a proof of that they carry an element of truth. And this means that the truth of theories, in fact, is temporary. It is validated by their explanatory and predictive power as long as this power is confirmed by experiments. So the theories are valid until something shows up which they cannot explain. And there was a big a situation of this kind which occurred at the turn of the century, the beginning of at the end of the 19th and 20th century. Something was wrong with the laws of classical physics, and there was a very famous lecture which was given by Lord Kelvin, who was a famous British physicist, to the Royal Institution in the year 1900, and he gave the following title to his talk: 19th Century Clouds over the Dynamical Theory of Heat and Light. So he pointed to the two problems which seemed to be very technical problems. The fact that the thermal radiation, the radiation of heated bodies, could not be explained. The spectrum of the light which was emitted by heated bodies could not be explained by classical physics, by Maxwell's equation and thermodynamics. And the second cloud was related to Einstein, who was a hero of the previous talk. The fact that light seemed to have the same speed whoever was observing it. If you are running along a beam of light, you still saw the light having the same speed as if you were motionless. In fact, the speed of light is independent of the observer. And this could not be explained. And Michelson, who was a famous American physicist, had made an experiment to try to measure the change in the speed of light with respect to the motion of the Earth around the sun, and he was not able to find any positive result. So these two clouds gave rise to quantum physics. The first cloud gave rise to quantum physics, and the second one to relativity, the special and the general theory of relativity we heard about. And the scientist who was at the origin of these two revolutions was the same man, Albert Einstein, with the famous papers of the year 1905, and the paper of the year 1915, 1916 about the general theory of relativity. So you see that, but what I want to say is that Einstein did not throw away Newton. He just found that Newton's law were an approximation. And when Einstein looked for the general theory of relativity, the main point that he tried to, which was guiding him, is that his new theory has to give the same result as Newton's law when you applied it to the motion of planets, up to a very, very small difference, which was also one of the proof of the general theory of relativity, which is a very small deviation of the motion of Mercury around the sun. But it has, in fact, Newton's laws are still valid. They are just valid in the domain where the velocity, where the particles have velocities which are small compared to the velocity of light, and in domains where the gravitational field are not huge. So it's not, the truth is evolving, but the truth is not, the previous truth is not rejected, is not annihilated by new theories, and this is very important. Now I would like to say a few words about the second point, which is proving scientific truth by its usefulness. And I want to give you a very simple example that everybody knows about, which is the GPS. The GPS is a system which allows us to find out where we are at the surface of the Earth with a precision of about 1 meter. And it is based on a swarm of satellites going around the Earth. Each satellite carries an atomic clock, and it's a very precise clock, which is based on the laws of quantum physics, by the way, and the clocks are synchronized with each other, and they send signals, microwave signals, to our cell phones or our GPS detectors, and by measuring the time at which we receive the signals from 3 or 4 satellites, by triangulation, which is a trigonometric operation of mathematics, we can pinpoint our position on the Earth with a huge precision. And this is a marvel of technology and of basic physics. Quantum physics, I mentioned it, but also relativity, because the time which is measured by the clocks going around the Earth depends upon their velocity. This is a result of special relativity. And even more strange, the time given by a clock depends upon its position in the gravitational field, in this curved space-time that Jocelyn Bell described in the previous talk. And this seems to be very esoteric, very far-fetched, but if you don't put the relativistic corrections in the software of the computer which analyzes the data, the GPS is off by kilometers and completely useless. So you see that I think this is a fantastic demonstration of the validity, the truth of theories. If you don't apply them, you lose completely the power of the systems that you are trying to use for navigation. I also want to say that the GPS is not only used for navigation. The GPS can be used to find the exact shape of the Earth. You know, we think that the Earth is a perfect sphere, but this is only an approximation. And this is more, of course, it's very exaggerated. It's not to the scale, but the Earth is a little kind of potato which has a lot of departs from an exact sphere for many reasons. And by the GPS, you can measure with extremely high precision, by this kind of triangulation that I was mentioning, the exact shape of the Earth. So you get something, you get another meaning of truth. What is the true shape of the Earth? And then the question is, why do we want to do that? So what are the possible applications? First, for navigation, but also it's important for geophysics, because we want to know what is the distribution of density of matter inside the Earth, which can be interesting for finding minerals, for instance. It's also interesting because you can study how the levels of the ocean changes due, for example, to the melting of the ice cap of the North and South Pole. And maybe one day it will be possible to predict earthquakes by the fact that the shape of the Earth is changing very, very slightly during the time which precedes an earthquake. So you see that basic questions which you are asking yourself because you want to know the truth about a problem might have useful applications. And in fact, I choose this example because it is related to a seemingly useless question which was asked by scientists back in the 17th and 18th century. The question was, what is the real shape of the Earth? It's not a sphere, but if it's not a sphere, the first approximation it would be an ellipsoid. Is it prolate or oblate? And the two theories, the two ideas were being debated. If the Earth is prolate, it has the shape of a kind of rugby balloon, it means that 1 degree along a meridian would decrease when you go from a given latitude to the North Pole, for instance. But on the other hand, if the Earth is oblate, 1 degree along a meridian would increase with increasing latitude. And so the question was open. The royal astronomer in the beginning of the 18th century was Cassini in France, and he was measuring the meridian by triangulation, the same technique as the one we use for the GPS, and he had the feeling that the Earth was prolate. But on the other hand, Newton and Huygens were finding theoretically that the Earth should be oblate because it's rotating, the centrifugal force of the fluid materials inside the Earth should give it the oblate shape. And there was also an experiment which was done by explorators which went from Paris to the coast of Guyana in South America, and they found that the pendulum was beating a little bit slower at the equator. Part of it was due to the centrifugal force, but another part was missing, and it might be due to the fact that the point at the equator was farther from the center of the Earth than in Paris. So the question was open, and the only way to find the truth is to do an experiment, to do measurement. And so the French Academy of Sciences sent 2 expeditions, one at the polar circle and the other at the equator, to answer this question by unambiguous measurements. And this looks very much like the stories that we heard in the first talk. We want to answer a fundamental question, and 2 expeditions were sent at 2 different exotic places in the 18th century. You see here the map which was drawn for the expedition to South America. It was an expedition in what is now Ecuador, and was a province of Peru, with a Spanish colony at this time. And La Condamine was heading this expedition, was measuring 1 degree of latitude from the equator to 1 degree south by paving the area with triangles. And he was measuring the triangles by using Galilean telescopes pointing to landmarks on the ground, and by measuring with precision the angle, not with the precision of 1 second of angle, but let's say minutes of angle. They were giving the shape of all these triangles. Then they had to measure only one base, one side of one of the triangles, and they did that by carrying a stick over 10 kilometers, making sure that the Indians were not stealing the sticks. There is a lot of very interesting stories about that, and it took them much more than the Eddington expedition. La Condamine spent 11 years in South America to do this measurement, and in the end, when they came back to Paris, the 2 expeditions wrote a paper for the journal, which was the important journal at the time, which was the Proceedings of the French Academy of Sciences. And you see here the title of the 2 papers. The paper of South America had a very long title, Short Report about the voyage made in Peru by the gentlemen of the Royal Academy of Sciences to measure the degree of the meridian near the equator and deduce from it the shape of the Earth. And it was the other title from Maupertuis, was sent to the polar region. And the result was that the Earth is oblate, and they found that the radius at the equator exceeds the radius at the pole by about 3 parts per 1,000. So it's about 25 kilometers more, which allows people in Ecuador to claim that the Chimborazo, the mountain in Ecuador, is the highest point in the world because it's much farther from the center of the Earth than the Everest. So is it useful, or it is just a useless truth? And the question was already raised at that time, and I just point here to 1 sentence in the report by Maupertuis to the Academy. And I translated it in English. He said,
The academy was thus split on this issue, the openness or porous of the Earth. Its own lights on this question have left it unable to decide when the king expressed his will to resolve this big question, which was not one of the vain speculations whose idleness or useless subtlety sometimes keeps philosophers busy, but a question which must have real influence on astronomy and navigation. So you see here, scientists were already sensitive at that time that they had to give a justification of their research by the use that the research could have in the future, and we still are in this situation. We have to always to try to explain why our basic science is useful for something. So this leads me to this very important point that basic research, which is curiosity-driven, and applied research, which is motivated by utility, are closely related to each other. It's very difficult, sometimes impossible to make the distinction between the two. And I will give you an example which will be discussed later on in this festival, which is the discovery of gravitational waves. So it weaves again, it goes again in the same direction as Jocelyn Bell's talk, which is the demonstration, the proof that one big idea of Einstein was right. In the general theory of relativity, Einstein said that the space-time is curved by masses, but if masses change suddenly in one point of the universe, it sends a ripple of space-time oscillations, which propagate through space at the velocity of light. And this event occurs, for example, when two black holes merge. When two black holes merge, there's a cataclysmic event which produces a huge amount of energy, mass being transformed in gravitational waves. And this is what happened when the gravitational wave antennas, which had been built in the United States, making what is called the LIGO project, detected for the first time one of these waves. And Barry Barish will talk about that, I'm sure, in his talk in this meeting, but I just want to point to one thing, which we were talking about 1 second of arc, which was supposed to be very small. But in this case, what this experiment observed is a variation of the distance of mirrors, which is 1 billionth of the size of one atom over a distance of 4 kilometers. And how this could be observed is because the lasers which circulate in these gravitational wave antennas are fantastically stable in phase and in frequency. And so you see here, I don't want to spend time on this, but you see here a sketch of the apparatus. A laser beam is split into 2 parts, propagating in orthogonal direction, reflected by mirrors, comes back on the beam splitter, and you can arrange the system so that you have a destructive interference on the beam splitter, but when a gravitational wave passes through space, it will increase a little bit the distance in one direction, decrease it in the other direction, and this difference is about 1 billionth of the size of one atom, and it can be seen with detection. What is, I think, also very interesting is that the laser, which is essential for this observation, comes from the discovery of stimulated emission, again by Einstein, almost at the same time that he put forward the idea of general relativity. So you see that this instrument, the laser, comes from basic science made by Einstein, and it took 45 years before this basic science resulted in the laser, and then it took another half century for the laser to be improved to the point where this experiment could be made. Einstein would never have believed that this experiment could be done, and this is, again, I think, a fantastic demonstration of the depth of what truth is in science. A few words about what I call the connectivity of the scientific truth. What I have said up to now can be summarized in this kind of diagram. You have nature with a lot of phenomena occurring in it. You can observe some phenomena. You can do some experiments. From there, you get some theories. These theories predict new phenomena. For example, stimulated emission was predicted from quantum physics and by Einstein. These new phenomena lead to new instruments, the laser, and the laser in turn can be used to probe in more depth the laws of physics. And so it's a kind of virtuous circle. And the side effect of all this is also that you develop new technologies. The laser is being used in many, many other fields, and you get more power over nature. And this is what I call the fabric of science. It's a kind of web which relates basic science to technologies, which also relate different fields of science together. And if you want to change something to this web, you have to be careful, because if you change it, you have the new systems that you produce has to keep explaining the phenomena that the old system was explaining to be more powerful, but you cannot reject things like the conspiracy theory do by saying, okay, this is not valid, I just change everything immediately. So you have, for example, the people who deny global warming and who say that it has nothing to do with greenhouse effect. They are just throwing away 2 centuries of science in thermodynamics and in chemistry, and they should have to do a lot of explaining for that. But of course, they don't care because they don't follow at all the scientific method for their stupid statements. So now a few words about universality of the scientific truth. As has been said before, the scientific truth, the same scientific method is practiced everywhere in the world, whatever the local particularism and the cultural habits. Modern science was born in Europe, and then it migrated to America, and migrated to India, to China. Everywhere in the world, we all practice the science with the same method. And you see that this global approach to science is able to survive even during periods of wars. We saw that the German and British scientists were working together and helped each other. It was a beautiful example, and I will give another one in a moment. And so this is very important. Also, I think that the actors of science, the people who discover things, in the end, they recede behind their discoveries. And this is one point I am not exactly, don't agree exactly what Jocelyn said. I think if Eddington had not been there, it would not change anything. Relativity would have been succeeded a few years later, and the demonstration of the validity of general relativity. I even goes further. I think if Einstein had died at the age of 4 from anything, somebody else would have discovered, because this is not an invention. This is a discovery of an objective law of nature. And I think that if on another planet there is a civilization, in an exoplanet civilization which has reached our level or went beyond, they must have discovered the relativity. Maybe they will express it by equivalent equations, different wordings. It will be a translation in another language. But relativity is something objective. I think this is a big difference. When you look at a Leonardo da Vinci or a Gauguin or a Renoir picture, you immediately know who was the artist who made it. So the artists invent their work. But if you think about quantum physics or relativity, you don't have to mention Schrödinger or Einstein. This exists beyond them because it's an absolute truth, an absolute statement. And also, I want to say very strongly that I disagree with the people who say that scientific truth depends upon the context, that the science is a cultural construct, as I say. Scientific truth does not depend on the cultural context in which it is produced, even if for some rather mysterious reason, some periods in the history of mankind have been very fruitful for the development of science. I think about the Renaissance time, or maybe at the period of the First World War, where Einstein and other people discovered a lot of important things about science. So, but if it had not happened at that time, it would have happened at another period. And the last part of my talk, I would like to say a few words about the fact that science has to fight against prejudices and biases of our intuition. This has a trivial aspect, but it has also a very subtle aspect, because even scientists have been caught into this problem. So what are the blinders of biases and prejudices we have to fight? In fact, we have to understand that as science has progressed, it has become more and more difficult to grasp because it goes below the surface of things which appear to be obvious. And you have a lot of counterintuitive things which come into play when you want really to understand what's going on. And I will quote, the first prejudice is the illusion relative to motion. Until the end of the Middle Ages, it was obvious for everyone that we were at rest in the center of the universe. We were there, so we did not move, it was clear. and everybody was seeing the sun rising in the east and going down in the west, so the sun was moving around us. It was absolutely obvious, and moreover, it was written in the scriptures, so we could not say anything against that. And then Copernicus came, and he said, no, that's not, this is an illusion. In fact, we are going around the sun, we are rotating, spinning and going around the sun. This explains why the sun seems to be moving, which is one good thing, but it also explains the motion of the planets, which, according to the old theories, were very difficult to understand. And Galileo immediately accepted Copernicus' ideas, and he was persecuted for that reason. And we all know what he said when he was on trial, and yet it moves about the Earth. He really wanted to state this. And I found on the internet, which is very good, another scientific invention, which is very good when you have to prepare a talk. I found this quote from Galileo to Kepler, which said, "What do you have to say about the principal philosophers of this academy?" I think he was talking about the Academy of Lincei in Italy, "who are filled with the stubbornness of an asp and do not want to look at either the planets, the moon, or the telescope, even though I have freely and deliberately offered them the opportunity 1,000 times. Truly, just as the asp stops its ears, so do these philosophers shut their eyes to the light of truth." They don't want to know anything about the motion of the planets. And in fact, I am sad to say that it's still the case. There have been a poll made recently in various countries, and there are 7% of the people who still think that the Earth is flat, and a lot of people who don't think that the Earth is spinning. In fact, I even saw on the internet a very interesting video which shows a fundamentalist Islamic cleric which explains by scientific argument. He said, okay, if we were rotating, we would just want to make a trip by plane to take off and to wait until the Earth is going below us and then to land. And since we cannot do that, it means that the Earth is not rotating. So you see that these people still have not accepted the relativity of motion, which was a big discovery of Galileo back in the 17th century. So this is one illusion. Another illusion is the illusion about the universality of time. People who believed in Newton's equation and Newton's vision of the world Newton assumed that the time was something universal. The time was elapsing exactly at the same rate for everyone in the universe, and all the motion of the planet, the stars, and everything on Earth were motion against this continuous and universal evolution of the time. And then came Einstein, and Einstein said, no, it is not true. The time depends upon your speed. Two observers are in a relative motion with each other will measure different times. And this is the fact that the time is the same for everybody is an illusion, because most of the time we travel at velocities which are so small that we cannot see this effect. And now, of course, we have atomic clocks, and I give the example of GPS, which measures this, and it is essential. And I mention this because it also relates to the previous talk. Jocelyn mentioned that the theory of relativity was announced to the English-speaking world by Eddington, but it had also to go to the French-speaking world. And the guy who did that was another scientist, Paul Langevin, was a professor at Collège de France, a very well-known physicist, who was not a pacifist, but who was a friend and a colleague of Einstein. And so he invited Einstein at Collège de France in 1922, and you see on this picture Einstein discussing relativity with Langevin at the Collège de France. And at the bottom you see Einstein exposing general relativity at the Sorbonne in 1922. And there was very, very animated discussions between the physicists and philosophers at that time. And one of the philosophers was Henri Bergson, who was also a professor at Collège de France, who did not challenge Einstein's theory, but he said, oh, this is the time of physicists. Maybe for physicists the time depends upon the observer, but for me, the time which I use for thinking and the time for my biological clock cannot be the time of physicists. And Einstein answered, I don't know what you are talking about. There is only one time, which is the time of my equations. And this was a very interesting discussion, and Langevin went into this discussion by describing his well-known twin paradox. Langevin used Einstein theory, special and general relativity, to explain that if you had two twins, one twin staying on Earth, the other one traveling at a very fast velocity through the universe and coming back on Earth after many years, if it was traveling at a velocity not too far from the velocity of light, he would come back much younger than his twin. And of course, there was a strong resistance against that. Bergson did not believe that, but Einstein is right. Now experiments have been done with elementary particles showing that the lifetime of a particle is considerably increased if they travel at a velocity close to the velocity of light. So in this picture, you see that at that time at Collège de France, there was a discussion between a physicist, a philosopher, by the way, Bergson got a Nobel Prize in literature, and a mathematician and politician. And I show here Paul Painlevé, because Painlevé was a mathematician who wrote many papers on general relativity, and he was also very important to promote the ideas of relativity in France. And I am sad to say that I don't think there is any politician in France now who would understand 1/10 or 1/100 of what Painlevé understood about relativity. So it was a very special time where a scientist was also a politician. And Painlevé, he had been prime minister and also minister of foreign affairs back in the 1920s, a very important politician. Third illusion of determinism. And this is something in which Einstein himself was caught. According to Newton, and if you know the initial conditions, if you know where the planets are at a given time and the velocity, you can compute everything in the future. And Laplace, who was an astronomer and mathematician in the 18th century, used to say that if you give me the position of all the particles in the universe and their velocity at a given time, I will predict the future of everything. And this was, of course, it's not possible because we don't have the power to compute. But what quantum physics tells us is that the randomness of quantum physics is more profound than its classical inability to understand everything. Quantum physics tells us that when an atom is excited, the time at which it will emit a photon or a radioactive particle cannot be computed, cannot be predicted. You can only predict the probability for the event to occur. This was understood by Einstein, but he did not like it. It was going against his own conviction. And during the discussion he had with Niels Bohr back in the Solvay conferences, he used to discuss about that a lot. And Einstein used to say, I cannot admit that God is playing dice with the universe. Of course, when he talks about God here, it's a metaphor. You cannot understand that the laws of the universe should be statistical, should be random. And Bohr used to answer, who are you to tell God the rules of his game? So, and this goes very deeply into modern physics. And I just give you an example on the next slide, and I think that Ignacio Cirac will talk more or less about that in his talk tomorrow, which is the notion of entanglement. The fact that if you have two quantum particles, each of them may have two states, which are represented here in blue and in red. When they interact, they can get into a state which is strongly entangled, which means that each particle loses its quantum identity, that the identity is only the identity of the two particles. And even if they travel through space at very large distances, this kind of influence at a distance remains valid. And what quantum physics tells us that a measurement made in one part of the universe, which is random, will have the same randomness as a measurement made at the other side of the universe. So this was too much for Einstein. Not only quantum physics is random, but it's a non-local randomness. And Einstein understood that very well. He described an experiment in which this happens, but he said that this cannot be the last answer. I just want to mention that this kind of randomness can be used in cryptography, for instance, and it's something which also shows the truth of science. You can use this to do something, you can employ this to do something useful. Einstein did not like this. He called this a spooky action at a distance. And he thought that quantum theory was incomplete. So experiments have since vindicated quantum physics on this point. and it's called Bell's inequality, and it has nothing to do with Jocelyn Bell. It's another Bell, which was able to put this discussion into equations, into a formula, and quantum experiments have proven that quantum physics is indeed, obeys indeed to these strange laws. The last illusion has nothing to do with physics, and I don't know anything about biology, but I think there is an illusion of creationism. What do Darwinian theory tell us? It tells us that organisms on Earth have evolved through random processes, random mutation, which are oriented by the competition of different species, and if a mutation is not positive, does not help, it disappears, and only the positive mutations give rise to the succession of generations. And this is very difficult to admit just by intuition, because it involves processes which occur over millions and hundreds of millions of generations, and we have no intuition about probabilities occurring at this scale. So people prefer to believe that there is some kind of intelligent design, some kind of God, some kind of creationism, which explains how an eye has evolved over the generation, over so many generations. And this is the illusion of creationism against Darwinism. Again, on the internet, I found a typical sentence of creationist people. They say, the whole issue revolves around whether we believe the words of God, who was there, or the words of men, no matter how qualified, who were not there. So what kind of answer can scientists give to this kind of statement? I think the only answer we can say is that science is not based on belief. That's the word we believe, which is wrong in the first statement. Science don't ask you to believe in something. Science just gives you some rules and tells you, if you apply these rational rules, we give you some observation which lead logically to consequences. And this is what science is about. So I think it's time to conclude, and I want to say a few words about the role of education. We have to teach science, to train young people to science, and this is obvious, and we have to do it in a way which triggers their curiosity, which makes them want to go into science. But it's not only science which is at stake, because when you learn rational thinking, when you learn the values of the scientific method, you can apply it to other fields and to other decisions you have to make in life. And this is, I think, very important. Condorcet was a mathematician and a philosopher in the 18th century, at the time of the Enlightenment, wrote a treatise on education in which he explains that. He said, if you want to have citizens of a democratic state, they have to be educated, because education will give them the means to be able to recognize what is the right way to vote, who is a good statesman and who is just a demagogue or a populist, as we would say now. So to defend the values of science and democracy, which go together, there is only one response. You have education at all ages and at all levels. And just to give a proof of that, a contrario, I would say, I would like to quote, and I don't like the person I will be quoting, as you will see immediately, I would like to quote a sentence by Donald Trump, who said, "I love uneducated people." And you understand why, because only uneducated people can be put in this kind of populist atmosphere. So I don't want to conclude, so I just erase this sentence. I don't want to conclude on this negative note, and I just want to say that history, and I think I have shown it, history gives us a hope that science will finally win. Because after all, who remembers the name of the Pope was against Galileo? Who remembers the name of the biologist who forced Stalin into this terrible agricultural experience which led to famine and to the fact that people died from hunger in Soviet Union. So I can give you the name. It was Lysenko, was against Darwin, but everybody remains Darwin, not Lysenko. And finally, who remembers the name of the Nazi scientist who said that Einstein's science was a Jewish science, And there are a few names, I won't give them, but there are a few very well-known German physicists who were against Einstein just for that reason. And finally, we remember Darwin, Galileo, and Einstein, and this is a hope for the future. Thank you very much.